So first of all, here are the people that I give, all the credit to as per usual because they did do all the work basically, and I'm just extrapolating from it. Right now we're on this stage over here, because I realize this is here now. Um, so we will talk about this, because there's an easier way to do the integral conservation equations, and I was doing it the hard way. Okay, I was going to index notation. Well, guess what? There is absolutely no need to go to index notation. And to solve this, I was shocked. I was incredibly surprised this is possible. So we all know the beautiful continuity. Like this continuity equation, I can never forget it because it's ingrained in my brain. Although I will say I do not know the polar form of this, which is what I need to do eventually. And let me just remove that so I can figure out where to talk. That looks good. But here we have this, all right? And then we have our beautiful, what's it called again? The content, no, momentum equation, which again is in my brain. I can't forget it anymore. It's a beautiful equation that's stuck in my head, and I love it. Love that it's stuck in my head. Honestly, the thing I love about what's again? The thing I love about fluid mechanics is that there's only three equations. Any problem really has those three analysis, but even more so for Stokes equation. No, Navier-Stokes equation. This is why I like Navier-Stokes equation because it's like three equations that define everything. I talk too much. Let's just keep on going. I am too talkative today. Now this force, they make a beautiful equation that you'll see, and I realize now that the fan is gonna make my recording bad. But what are you gonna do? Make the person that did it pay? No, can't do that. Anyways. And as you can see that this is basically V over density dt. I love when things get easier. And this is definitely easier. Oh, I forgot to write V over here. Oh, yeah, V. Yeah. And you can multiply this by V because you can. Anyways, so far so good. And then you do plus gradient dot density VV equal, this is that, basically with a V. Equal negative gradient p plus gradient dot tau. And from this, you can get the integral form, which is divergence theorem. That's super easy. I should just do it for completeness, but you already know it. It's basically d dt because of how the uh the system works. You can do this quite easily. And then over here, we're gonna use actually we'll write in volume form first because you're supposed to use volume form first. Yeah. Okay, we have everything, right? And this is the first use of divergence theorem, beautiful divergence. We all love divergence, to be fair. I mean, I don't think anyone can argue with that because a volume integral is a triple integral turning into a 2D integral, which is so much easier than a 3D. Like, imagine doing a triple integral. That yeah, that's a pain. A volume integral is hard. Let me just say this. Well, a surface integral is hard, but not impossible. Let's just say that. It's still hard. I mean, it's still you can make a question with an insane like geometry like this, and you can never solve it. I mean, you can give me that geometry and with fluid properties here, and I can't solve it by hand. I need a computer. Anyways, here we go. Beautiful, beautiful. And now the energy equation. Yes. Now the energy equation is the exact same, and I think he already talks about it, but we should show it off. So. The secret is again continuity. Like it is E plus V squared divided by 2, and you put continuity here, density, and plus if you see me sniffles because I have some allergies, but that's neither point here, not the point here, so we'll just keep on going here, and then yeah, and I hope it's quite evident I'm using what's the right word? I'm using I'm using shorthands here with the tensors over here. This is a dyadic. I forgot. It's a big ass tensor. We can talk about it, but I always don't like to expand the tensor because then it becomes like a pain. But that's a tensor. That's a higher order tensor. Another way to write that is Vj, Vi, which is probably more helpful for you because with index notation, you can just see V1, V1, V2, no, V1, V2, V1, V3, and V 2 1, V 3 1, and V 3 2, and so forth and so forth. With index notation, you can visualize the numbers and easily get them. So, yeah, if you want to expand it, go ahead. Be my guest. You will get the same thing when you dot product because if a second order tensor is dot product with a gradient, it turns into a first order vector. And yeah, that you can give all credit to Dr. Sanchez on that one and Dr. Centillion. And yeah, they did teach me that. It's looks like it's more complicated, which is fair enough. I mean, it was always going to be more complicated because it has negative gradient dot v plus this tensor, which is going to be a little bit of a more I don't know how to do before, so I'm going to have to figure that out a little bit. But I think I do know how to do it. It's not that painful actually now thinking about it. And then there's going to be another term over here. That's wrong. Give me a better version, please, please. Sorry about that. My tablet is not cooperating with me right now. So anyway, gradient dot parentheses gradient kt. Is that right? We all know that's not right. Parentheses k gradient t. Beautiful. Now, what do we do here? Well, we can add the continuity equation. Clearly, that's true. We can also add the momentum equation. And if you don't know why, I will explain a little bit. So, why is this possible? What did I do? This is a common technique that people used in the olden days. V dot dv dt. That looks like it won't give me anything. Well, look at it in the sense of v dot dt. Well, look at that. It is gradient v dot vt plus v dv dt. Huh, isn't that 2 v dv dt? And I know I'm not doing it carefully, but this is all index notation as usual. And with that said, that would indicate that's 2 v dot gradient v dt. Huh. So if we divide by 2, we get the original result, which is a common thing that people use. So index notation for the win on that one. You can also prove it a different way. I think Dr. Sanchez has an easier way to prove it. Yeah, I'm 100% sure he does. Because I'm using the index notation way, which so then, yeah. Anyways, after the v, let's do it the Dr. Sanchez way, which is this. There you go. There you go. We can't complain about this. This goes to 0 anyways with the dot product. And then we have gradient v squared divided by 2. So we have v dot gradient v squared divided by 2 parentheses, right? And then we have equal to negative v dot gradient p plus v dot gradient dot that. Huh. Beautiful. Now it's a scalar. We can add things together. Yeah, dE dt. What's density there? I forgot about the density. Oh well. You guys caught that, right? Anyway, density V bar. If you realize why if it looks sloppy, it's because my pen is out of battery again. Yeah. I'm trying my best with this pen, okay? V squared divided by 2 divided by dt plus v dot gradient v squared over 2. And I think it was v plus v dot gradient e equal now negative p gradient dot v negative v dot gradient dot p plus v dot gradient dot tau plus tau dot gradient v plus gradient k gradient t. Oh, this is large. I didn't expect it to be this large, but we got something here, as you can see by our beautiful equation. Okay. So next, we're going to simplify this into this form density d dt parentheses e plus gradient squared divided by 2 plus v dot gradient e plus v squared divided by 2. And this is where we get tricky over here. Now understand that this is something index notation. If you don't know, this is a dot product. Yes, because it's a scalar. And then let me show you what I mean. If I were to give you what do you call it? I think it was negative gradient parentheses dotted with density V, right? That was density V, no. It was pressure P. Pressure. Density Xi, P plus VI, right? Negative, but that doesn't really matter. We'll just put negative on here. And then this will give me, if I remember correctly, density Xi, P with a VI on the outside, and then it'll be density VI, Xi with the P out there, which is this form. So you can just add it and say it's negative gradient dot parentheses PV. Okay, you got that? Next one is this form over here, which is a little harder, I must admit. But it's the same idealized reality for that one. I believe if you do what I call uh let me just do it. Gradient yeah, let me just do this. Let me go to indentation again because I'll need it. So again we'll do erase this portion for now. And let's prove this real quick. Oh, this is gonna be hard. So it's gonna be what's it gonna be? The final result is going to be density xi with parentheses. What is it again? It was v I. Yeah, this doesn't make sense. What's going on? Oh, I know how. I know how. Tau ij, and this is supposed to be a j over here. J, which if you do the index notation way, vi plus tau ij. Oh no, that's wrong. Tau ij divided by xj vi. And this over here, I believe, is gradient dot no gradient. What is this? Is gradient v double dotted with tau. So yeah, that's right. And this over here is it is v dot tau dot no gradient dot tau dot v, which you get this form. So this is actually gradient dot dotted with tau dot v. I think I did it the opposite way, but if it's symmetric, it doesn't matter. But I think it does matter here. So and then plus gradient k t. Now, with that said, we have one last thing to do before we can call it the full conservative force and the density. Yeah. I mean, we already have density, although. Yes, we do have density, but we need the other time variant density for the tau for it to be changed to entropy. Yes, sir. We're so close. Yeah. I think we did a good job. I'm double checking to make sure I am doing this correctly. Yes. Now we have to add in E plus gradient V squared divided by 2 parentheses by d density dt plus E plus V absolute square divided by 2 V dot no gradient dot density V equals 0. So if we add those two up, what do we get? These are a dot product, so we get d parentheses E plus V. No, let me just show you. You want me to write it again? Probably. Let me just rewrite this whole thing again. Because repetition is king. I always say this, but repetition is definitely one of the kingpins of all engineering. So as you can see, I will also be changing up my notation for the absolute V squared because I get bored of one of them too. Yeah, definitely doing that because of that. And this is actually okay. There we go. We have our beautiful. This is also a dot product. Yes, that's a dot product. So we get gradient dot density parentheses E plus V squared divided by 2 equal, oh, I put the parentheses there, and then negative gradient dot PV plus gradient dot to v dotted by tau plus v gradient k gradient t. All right, we got that. Now realize if I divide this by density over density p and move it aside, you can get I believe it was called entropy, which I was shocked by. I mean, you don't see entropy every day. So this form turns into h plus v squared divided by 2 gradient dot. So we have a beautiful, beautiful equation for that. Now we integrate. Now, when we integrate this one, dv, we get the form of d dt parentheses to d and e plus v squared divided by 2. And we know this goes to 0 steady state. Oh, wait, integral, please. I didn't write the integral. Over here, we can do the n thing with the density. There's density here. There's density inside. So you can, what is yeah, it's a v. I think I'm missing something. This doesn't work. Ah, there's a V here, I think. Yes, there's a V over here, so this is V. My mistake. There's a V there. So then there's density parentheses E plus there's a V here too. V squared divided by 2, and it's V dot N dSS. Oh no, I already made a mistake again. We already moved the pressure to the other side, so we can just get rid of that. It's over here. And then this is plus integral it'll be tau parentheses, no. Tau dot v dot n ds, I think. Am I correct about that section? So we're moving on to shock.